Moving on then with the topic of current of electricity. Um, First of all, looking at power, we've already covered some of the ideas to do with power in the first of the assignment sheets. Going back to our basic definitions, potential difference V equals W divided by Q, and current I equals Q divided by T. If we take those two quantities and multiply them together, V times I, we get W divided by Q multiplied by Q divided by T. The Q's cancel out. And what do we end up with? W divided by T. And from our earlier work in terms of mechanical energy and that sort of thing, work done divided by time taken is defined as power. And so therefore in electrical situations, power is equal to potential difference, or voltage if you want, potential difference, multiplied by current. Power P equals VI. And the units of power, as we've dealt with earlier in the year, are of course watts, capital W as a symbol for the watt. Here's an example, 3 bits to it, so I'd like you to, after you've made the note about power from the previous page, copy out this example and work your way through it. Now, the first formula for power, V times I, is useful if you know what the potential difference is and what the current is. But you may not know that. If you've got a resistor, it's potentially possible that you know the current and you know the resistance. So let's look at a formula you could use if you just know those two things there. So let's start with our formula. Power equals V times I. And then if we use this formula here, V equals IR, which comes from our definition of resistance, we can get that power is equal to, let's get it right here. Instead of the V, we put the IR in. That's correct. And then we multiply that by I here. And so what do we get? We get that power is equal to I squared R. I think I have a student having just come here. Yes. Come on, Matthew. Come to do a catch-up DDR test. I'm just making a video, Matthew, but everybody can hear that I'm doing that. That's okay. There you go, take it out the back. Or you can sit there and listen if you want. Okay, continuing. I'm not going to let that interrupt what we're up to. Matthew, you're famous. Power equals I squared times R. Okay, so that's interesting in that if you have a resistor then with a current going through it, if you double the current, you don't get twice the power, you'll get 2 squared or 4 times the power. The third possibility is that you have a situation where you've got the potential difference across the resistor, V, and you know the resistance, but you don't want to bother working out the current separately. So in that situation, then we have power again equals V times I, but this time we substitute for the current. And so we have V times the current, where the current comes from, once again, this rearrangement of the definition of resistance. So we get V times V over R, and so we end up with power equals V squared divided by R. So it really depends what information you're given as to which of the 3 power equations or formulas is the most appropriate one to use. I do find this one here, power equals I squared R, quite informative in figuring out what's going on in a resistor when you change the current, particularly to do with this idea of the I squared in that. All right, an example there about a transmission line, a power line, carrying a relatively large current, and the wires that make up that line have a resistance of 0.15 ohms, and I want you to calculate the power, the rate of energy loss in the cables there. Then on the other side of a transformer, we've gone down to a much lower current. We're going to have wires of the same resistance. I want you to figure out what happens when you make that current smaller. Does the power just decrease by a factor of, 200 divided by 5, or is it different to that? So you work through that and see what happens. All right, factors affecting the resistance. So let's say we've got a bit of wire, all right, like so. What are the things that are going to affect the resistance of that wire? One of them is what it's made from. Now, the property of the material that expresses that is known as the resistivity. Not resistance, but resistivity. It's a property of the material that depends on factors like how many electrons are available inside the material, that sort of thing. So it's represented by the Greek letter rho. Okay, R-O-E, Greek letter rho, like a curly P. Okay, so that's the resistivity of the wire. Other things, I think reasonably obviously, the length of the wire. If you make it longer, that's going to affect things. And the other one is the cross-sectional area of the wires. We're going to take those three ideas and bring them together and express them as an equation. All right, so we've got resistance. Turns out that we say it's proportional to the resistivity. If the resistivity is higher, then the resistance is higher as well. And that resistivity too of a material does depend upon things like the temperature. If you heat the metal up, you'll find that its resistivity increases. Also, we can say that the resistance is proportional to the length of the wire. And the other one, to do with cross-sectional area, if we make the cross-sectional area, so we start with that and we make it larger, we've got more area through which the charges can pass, and therefore it's easier for the charges to go through. So the resistance is inversely proportional to the cross-sectional area. Those three ideas are taken and expressed together by saying that R equals rho L divided by A. And what would the units of resistivity be? You could figure that out by rearranging this equation and making rho the subject. Rho equals RA divided by L. And so what are the units of that going to be? They're going to be ohms. Area would be measured in meters squared. Length would be measured in meters. And so what do we get? We get that the units are ohm meters, and that's how you leave it. You don't need to worry too much about what that really might mean. Just leave it in that form. All right, another example for you to have a go at then, using this formula then. So we're saying R equals rho L over A. So in this particular case, you're asked to work out the resistivity. You can do that. Something's just gone wrong with my pen here. There we go, rho equals, and work out the resistivity just by rearranging the formula. I take note that the cross-sectional area is in millimeters squared. So you're going to have to figure out how to convert from millimeters squared to meters squared. And it's not just a matter of a factor of 1,000. All right, think about that. Ask around if there's others who are not too sure. I'll give you a clue. Okay, give you a clue. Here you go. There is a meter by a meter. Figure out how many millimeters squared there are in there if you divide each of these meters up into millimeters, and that's going to be the factor by which you have to change things there. And then a second or a continuation of that first example. And I will be putting solutions to these examples up separately.